today, solutions and colligative properties, and in your notes you may have kind of leafed through and looked at it. I've broken this down into two parts. I really don't know why, but this first part deals mainly with solutions, and then the second part deals with colligative properties, which we haven't spoke about yet. Solutions we've discussed a little bit earlier on. We talked about what a mixture is, what a pure substance is, what a homogeneous solution is. And again, I don't know if you remember from back in the day, and I really can't even remember when we talked about it. So here's an example where I have this Erlenmeyer flask, and it has some sand and water, and it looks like it's making some moss in there. Is this a solution or a mixture? And before we go too much further, what is the definition of a solution? What's that?
It's something dissolved.
Kind of, yeah. Also, when we talk about solutions, things are evenly dispersed throughout. And I don't have to do anything to get those particles to be evenly dispersed throughout. So as I look at this, are all the things evenly dispersed throughout? No. So this is by definition a mixture, or a heterogeneous mixture.
So if you can like see the different layers in this formation.
Correct. Now, here's an example, and again, I don't know why I shook it up, didn't need to, but here's some copper sulfate that looks kind of grungy because I think of all the dust. But is that a solution or homogeneous or a heterogeneous mixture? Solution. Should be a solution. It should be a lot clearer. There's some gunk in there. So when we talk about solutions, I need to throw that out. So when we talk about solutions, another example that I spoke about earlier is air. How we have oxygen, nitrogen, carbon dioxide. And all those things are evenly dispersed throughout. That's a great example of a solution. But a mixture, the only way to get these things is to shake it up. And while I'm shaking, the things are evenly dispersed. But as soon as I stop, the heavy things, boom, to the bottom. But then we have this kind of muddy water situation. But will it be that way in an hour?
No.
No. If I come back a day from now, it'll return back to this later on. So again, this is an example of a mixture or a heterogeneous. That would not be funny. That would be sad. And I've had these, I made these up 15 years ago, so I'm kind of impressed on.
Wait, what's in it?
Just water and some dirt that I got out of the backyard. I think one of them has a dog hair in it, so that gives those little microorganisms something to snack on. I don't know. It's a closed system there. Have you guys? Did you get all the blanks there?
Yeah.
Okay. Let's see. Trying to remember. Oh yeah, solvent, solute. Do you recall talking about solvent and solute?
Yes.
Okay. So the solute is what? Is that the thing that's dissolved or the thing that does the dissolving? The thing that's dissolved. Good. So the solute is the thing that gets dissolved. The solvent does the dissolving. And some of you may have heard the term before, water is the universal solvent. However, it doesn't work very well on things that are like oil-based paints, other things that are quote-unquote non-polar. So the reason why I have this is because the oil on top and the water with some food coloring on the bottom, the food coloring and the water like each other. However, the oil doesn't like either of those because these are polar compounds and these are non-polar, so that when we jostle those around, they don't like to be with each other. But as soon as you mix it up, okay, that's when the fight begins, and now we have our little strawberry slushy, so to speak. But after a while, again, this is an example of a mixture. They seriously hate each other so much that they just get away from each other. So we'll have those division layers back again. Back. Okay. The process of solvation. Hallelujah. All right, when we talk about things that are being dissolved, here's an example of a water molecule. The water molecule is made up of 2 hydrogen and 1 oxygen. We've talked about the charges associated with the water molecule, how the oxygen has a -2 charge, the hydrogen has a +1 charge, but we have 2 of those. There's what's called a positive end and a negative end to the water molecule. And it's based on that positive and negative end of the water molecule that will allow certain things to dissolve or not be dissolved. So some things are not really affected by water molecules, like oil-based paints, where if I had, say, some salt crystal, okay, like in this case sodium chloride, when I place sodium chloride into water, okay, just like our oceans, it is soluble. It'll dissolve in water. It'll actually dissociate, and what it'll do is it'll dissociate into ions. And you'll notice that if we're looking at a positively charged particle, how the negative end of the water molecule faces toward it. So whenever you hear the term something is aqueous, and we've talked about it a little bit, but I don't think we've talked about the mechanisms with it. What that means is it's attached, there's some water that's actually surrounding it, and it has certain ends that are attached to that particle. So if I'm looking at a positively charged, the negative end is attached to it. If I'm looking at a negative particle, then the positive end of that water molecule is attached to it. And what it'll do is it'll pull those particles away from each other to help dissolve it and make it a solution. If I have too much salt, so there is an upper limit to how much stuff can dissolve in water. And there are things that really do a nice job of dissolving in water or dissociating in water. We'll talk about the difference of those two. And then there's some things that once you drop it in, won't dissolve very well at all. And that goes back to our solubility rules, and you'll get to revisit those. I don't know if that's today or not. But I always use this example, and I'm not talking bad about my wife. I love you, dear. But whenever we go out and eat, she always gets iced tea, and she always rips open 2 bags of sugar, pours it in. And as the sugar's going in, you can see it disappear because it's dissolving. But then inevitably, she always grabs 2 more, and I'm like, don't. She does it anyway. Drops 2 more bags of sugar in there, and you can see the crystals stay intact, hit the bottom, and bounce around. Why? Because they haven't dissolved. That solution has dissolved as much sugar as it's going to dissolve. It's at the upper limit. So all that other sugar just sits on the bottom as crystals because there isn't enough water that wants to break that down. Now, is there a way that I could dissolve that sugar?
Stirring. Add more water.
Add more water is one way. Stirring it won't do it. It'll look like they're getting dissolved, but then they have been inevitably stopping. Increase the temperature. So if we heat it up, and that's one way that you can make rock candy. If you've ever had a chance to do that, it's a mess, I'm going to tell you right now. But if you want to make rock candy, then what you do is you get your water, you boil it, you add a lot of sugar in there, let it dissolve. And then as it cools, then the mess begins. And you start to see these crystals of sugar coming out of solution because we actually were able to dissolve more sugar at a higher temperature, but as the water cooled, the water's like, I can't handle all this sugar. When we talk about dissociation, okay, we're looking at, number one, it has to be an ionic compound for it to dissociate. If it's not an ionic compound, the compound will not dissociate, but it will dissolve. So examples of things that only dissolve but don't dissociate are things like sugars, organic compounds, things that are only made of non-metals. So, and when we look at some of these ionic compounds, it may appear that they're dissolving, but really they're dissociating. And then sometimes I'd even let you get away with saying, all right, the salt starts to dissolve and then it dissociates. So make sure you know the difference between dissociation and dissolving. If sodium chloride only dissolved, what that means is that we have our molecules. We'll say this is a sodium chloride molecule and here's another sodium chloride molecule. If it dissolves, it just breaks the bonds that holds those 2 molecules together. When we dissociate, we take the ionic compound and we break it into its ions. Now here's the thing that we have to remember. When you dissociate something, it will have a charge. So you have to show me the charge. You do not have to show me aqueous, okay, the state that it's in. So you don't have to go from here to here to here by showing solid, aqueous, aqueous. If it has a charge, you're telling everybody that it's been dissociated. We talk about molecular solvation. The bad news is, I've already said it, things don't dissociate from molecular compounds. And again, a molecular compound by definition is something that is only made up of nonmetals, or it's an organic compound. That's probably the best way to state that. So if we have things that are made up of just nonmetal with nonmetals, then there won't be any dissociation. Yeah, the thing I really want you to get out of that is molecular compounds. How are you going to recognize that it's a molecular compound? There's no metal. And how are you going to recognize that there's a metal? Well, it'll either be from group 1A, 2A, or that'll be the big ones for whatever reason. And I think you guys know what metals are at this point. All right, miscibility. When we talk about miscibility, it's just another way of discussing how well something dissolves. This term here, like dissolves like. If you go very far with your chemistry career, you'll get used to hearing this term over and over again. Like dissolves like. In other words, polar compounds dissolve other polar compounds. Nonpolar compounds dissolve other nonpolar compounds. Now again, I would not ever recommend you do this, but if you're ever painting with oils and you don't have any turpentine or paint thinner, what's another thing you could use that's probably around the house?
Water.
No, water's out. Gasoline, very good. In other words,
Are you crazy?
that's what I'm saying. I wouldn't use gasoline, but it is a non-polar compound that would dissolve another saturated solution, unsaturated solution. When we talk about a saturated solution, that's when my wife adds the third and fourth bag of sugar. In other words, the solution cannot dissolve any additional. Unsaturated solution means that it is able to dissolve more additional material. Okay? So saturated and unsaturated. Now I'm not talking about the types of fats, saturated and unsaturated. That's a whole different ball game.
Saturated is
Okay.
bad.
Okay. We'll talk about that in organics, so I'm not going to worry about those. Measuring solubility. I'll actually give you a chart. We won't actually measure the solubility here in class, but you'll be able to look at a chart at a particular temperature and say, ooh, that's saturated. No, that's not saturated. Okay, so we'll be able to look at that. When we say something soluble, you may hear me use the term, especially later on, if you take AP Chem, we'll say that, oh yeah, sodium chloride soluble. What that means is if I have more than 0.1 mole of that solute that can dissolve in a liter of water, we consider that to be soluble. Okay, so that's just a term. All right, and we talked a little bit about this already. Some factors that could affect solubility. Temperature. You increase the temperature, you increase the solubility for solids and liquids. That's a reverse for gases. Okay. In other words, I don't think we think about gases very often when we're talking about solubility or something soluble. But when I drink Diet Coke, has anybody ever drank a cola or like colas? Yeah? No?
Yeah, that sounds like a beer.
Okay. No, it doesn't sound like a beer. But do you like it when all the fizz is gone? When it's flat?
Yeah.
No, you
Yeah,
want
it
it to be all
stinks.
carbonated.
Carbonate, which means that you have carbon dioxide in there.
So the streamer things and slime off. You know what I'm talking about?
Okay. So, when we talk about gases, as the temperature increases for that solution, the ability for that gas to stay in the solution actually decreases. That's one reason why we typically refrigerate our colas, because we want that carbon dioxide to stay in the solution. All right, pressure. Again, the solubility of the gas depends upon the pressure acting on the system. When we talk about a closed system, that means that no gases are able to escape. So we can actually increase the solubility if the temperature increases, because it'll go back into that solution. If it's an open system, that allows gases to escape. That's one reason why it's much better if you're drinking your colas to have that screw cap on, not a can. If you're drinking with a can of cola, you better plan on drinking it within the hour. Okay. or half hour or 10 minutes.
Or put it back in the fridge.
Well, if you put it back in the fridge and let it sit there overnight, it'll get flat because the gases are able to escape.
They have little bottles of coffee, you can have one.
I've seen.
I don't really believe all this.
The best things ever.
All right, the homework, the ones. Now,
Oh my.
I don't want to do, now hang on. I don't want to do 1C for you, but I would like to do some examples similar to 1C. Okay, so let me do that real quickly here. All right, here's a couple examples that are similar to 1C. Here we have magnesium carbonate. And what's the question say for 1C? What's the... Okay, so write the dissociation reaction for each of the following. So I want you to tell me how that dissociates.
Mg.
Okay, so Mg, what's the charge?
Where's my periodic table?
There you go. I think we have the correct.
It's
Negative
plus 2.
Plus 2.
Plus 2 or negative 2? Plus 2. Metals are positive. And Lauren, would you say the other one was?
Uh-oh.
Was it you said it?
It's carbonate.
Carbonate.
Sorry.
But I don't know the charge.
Well, here, let's do this. If I have one magnesium and one carbonate, what must the charge be?
Negative.
Negative 2. So always use that as
What?
a key. Huh?
Oh. Never mind.
All right, and another one?
That's like a bad mistake.
Now, the reason why I want you to be able to show these is for what we're going to do next week, which is kind of neat. So how does this break apart? Or dissociate?
Sodium.
Sodium.
Into.
So, sodium, I hear.
Nitrogen.
Sodium. Now, again, these are all ions. So what do I put in front of sodium? Do I leave it or put anything there?
3.
3, good, because I have 3 sodiums. And since these are all dissolving in a solution, we're not making any gases. This will be nitrogen with a negative 3. Okay. In other words, these are all being dissolved in a solution, okay? So like, for example, this solution here is made up of copper sulfate.
So we don't need to worry about diatomics.
No. That's only when it's in its elemental state. So the copper sulfate that I had there, how would that break apart?
Oop.
Cu, what charge? This is good. This will get you back
It's a
into...
plus 2. Because sulfate has a negative 2.
Good. And sulfate has a minus 2. Okay. Beth, you all right, girl?